topic is called chain rule. The chain rule 2.5. They asked the one students remember from calculus 3 with fear in their eyes. When you ask them, do you remember chain rule? They're like, oh, I hate it so much. But it's extremely important, and it's the last hard rule of differentiation we need to learn. That's it. After this, you're good in differentiating skill. The chain rule. It's called a chain rule because it has chain reaction. Motivation is if I have 3x squared plus x raised to the cube, how to take derivative of that. Do you have any ideas how we can do that? I mean, the way you know. Yeah?
First, we can just substitute t for 3x squared plus x.
So we don't know chain rule yet. That's my question. We don't know it yet. We're just gonna cover it right now. So if you don't know chain rule.
Yeah, that's what I'm saying. We can just substitute t, and then we can just differentiate it, and then we can substitute t back in the equation because we don't know chain rule yet. So
yeah, surprisingly, it's almost gonna work, but a little bit not. Very good answer. I'll show you why. There's one piece missing there. But do you know how would you do it on a test if I ask you?
I guess you do product rule.
Product rule, right? And you can do 3x squared plus x squared and then use the formula there, or just 3x squared plus x, 3x squared plus x, 3x squared plus x. Too long. What if it's to 5 to 11? That's where chain rule comes in. I like this explanation I saw. Chain rule zooms into a function to see how the initial change, let's call it input, small input, can affect the final result output. That is sometimes called sensitivity analysis. Let me check if I'm recording. Yes. Sensitivity analysis is when you build an amazing model of how your rocket gonna fly to the space. The people are gonna ask you, can we make some details a little bit cheaper, or can we add a little bit less fuel to it? That's sensitivity analysis. What if you tweak a little bit? Tweak means change by a little bit some of the inputs. Will the output still be good enough? And you're like, yeah, actually a couple of screws can be changed into alumina or whatever. Or it will completely mess up everything. So in computer science, you tweak a little bit, everything doesn't work anymore. So usually that's a very hard job. That's what they know debugging is so challenging. But in applications, biological and medical and engineering and physics applications, that's important to know. Should I add a little bit more food to the population of rabbits in the farm or take a little bit off? Will it change the result too much? Will they die? Will they produce less because there's lack of food or not? Chain rule does a little bit of that. Zooms into a function to see initial change by a little bit, how the output will affect that. And also it works on the nesting of function, not nasty, nesting of functions. So f has inside a function, let's call g. G has inside of a function, let's call it m. AM depends, say, on a parameter t. We're going to learn parameterization soon. T, let's say t is time. Everything depends on time. How would you find f prime? Find f prime. And this is what chain rule teaches us, how to work with functions inside of the functions, which most applications have. None of the applications have a pure function. Your skin color changes with respect to the speed of your breathing, the temperature of the room, your personal temperature, and do you have a fever, you feel well, or you are shy. So all of this means function inside of the function inside of the function. And we need to know how to find how fast the skin of your color changes right now. That's derivative. How to do that using chain rule. And I'll show you the theorem. And I will mention some cool applications so you feel happy. The theorem. The chain rule says, if a function f and the function g are differentiable, let me write down this word again, differentiable functions. What does it mean to be differentiable? Who remembers? At least vaguely, what does this mean? Differentiable functions, what are they? You're able to take derivative. Agree? Yeah. Differentiable functions have derivative at the point or everywhere, wherever it is differentiable. Good job. And then we have composition of functions. Let me have more space. Composition of functions, we teach that in pre-calculus class, but I don't require you to remember it. I'm going to show it to you right now. Little circle, G. That's called composition of functions, or it's called a composite function. Composite function. That means, let me remind you pre-calculus class, f of x has f outside, g inside, and g depends on x. So f depends on g, g depends on x. That's what nesting is, a stuff inside of the stuff inside of the stuff. Composite functions always start from the right. The right one goes first. So if you have 3 composite functions, you go from the right to left. The very left one is the outside one. Then the theorem says that f, which is a composite function, also differentiable. Let me just short it out, differentiable. And we can take derivative of that composite function. And derivative has a formula. F prime of x is, you take derivative of the outside function. I'll be saying those words a lot for like a month. Actually, even in calculus 3, I remind students, take the derivative of the outside function at inside function. So you copy the function inside. Don't touch it yet. And then you do times, that's the chain rule, times take derivative of the inside function. It looks kind of sketchy right now, but we're going to do so many examples that you will get used to. Put this in the box. Today I was observing someone teaching this class, and they use df dt all the time, so I thought I should also start using it more often. But I want to sign first that in red color, f, the f prime, this, let me see, this, that's too thick, called outer function or outside function. Outer, right? Outer. Outer, and you take derivative prime. I call it outside function because outer is hard to say. At inner function. So we copy inner function. We just copy it inside of the outer function. But then you do times, and you should not stop. You never differentiated the inner function, so now you're going to differentiate and you multiply by the derivative of the inner function. So outer prime at inner times inner prime. And that's how you can see. Where, maybe I can write this down, that we had original function look like this. Equals, oh, let me also make this cute thingy here. Yeah. When the original function was f at g, and we're doing prime. So that's what we're trying to do. Derivative of a function that has function inside. We also call it capital F if we're too lazy to write down the function inside all the time. Again, it will get easier with more examples I show you, but the idea is, I like using Russian dolls, which I actually have. I'll bring them on Wednesday. I think I left them in my office. Russian dolls called matryoshka. It's a doll inside of the doll inside of the doll and so on. It's a very good explanation. People sometimes explain it as onions, the layer inside of the layer inside of the layer, or Russian dolls. So here is the outside Russian doll. You can make it pretty if you want. And that one is called F. Actually, this one should be red. If you want to be consistent. This is F, because F is outside. Here it is. It's outside. And then it has inside function. That is also a Russian doll. It's also a function, just a different one. That's G. And they both depend on X. So here's your Russian dolls. And you have to take derivative of the outside first before you get to the inside. So order matters. And that's what we're going to be doing. And it's going to be pretty fun experience. You'll be good at this, you want it or not. And then all the stem signs depends on the chain rule. That's how important it is. Everything that is happening in AI machine learning, engineering, physics, space science has chain rule in it. That's how cool it is. That's how important it is. So let's do some examples. We write the example, 3x. Oh, actually, let's do the one with square first. 3x to the 7 plus x, everything squared prime. Let's find derivative of that. And while you're writing down, I will tell you that Russian dolls are now only important for tourists. So nobody, not my generation, my parents' generation, did not own Russian dolls. It's a very not popular toy for a while. So they only exist for tourists. When you travel to Ukraine, Russia, Poland, Belarusia, they will always try to sell you Russian dolls. Because tourists need to bring something home and say, I bought a Russian doll. And they show the Russian dolls on the table. Yeah, nobody plays with them for a while, for like a century. So it's ironical, they only exist for tourists. And they all made in China. So it's kind of, the whole tourism part is kind of hilarious. Okay, let's try that. What is your ideas before we start jumping into chain rule? How should we do that? Someone already mentioned kind of good idea before. You had it in the exam. How would you work this out? It's 3x7 plus x squared. Ideas? Square. Let's square the square. That is a very good idea. So I will not differentiate yet. I will use the formula and change the input. Square of 3x to the 7 will be 9x. 7 squared becomes, well, not 7 squared. X to the 7 squared becomes 14. Thank you. Plus double product, which is 2 times 3, which is 6. X to the 7 and 1, 8. Plus square the second term, that is x squared. And now we differentiate that. And guess what? We're going to just do that. Did you remember this in the homework? So we're going to differentiate. 9x to the 14 gives you derivative. 1 what? 126 x to the 13. Agree, disagree? Correct, not correct. 9 times 14. Very good, good job. Fast calculation. Plus 6x to the 8, people at the back. 28x to the 7, thank you. And x squared is 2x. 48. Oh, good job. 48 x to the 7 plus 2x. I did this on purpose so that you pay attention. I always say that. And that is the answer. You're good to go. Amazing. No need to do anything else. So that is kind of time consuming. What if you have higher powers, lots of calculations, sine and cosines? So that was way 1 with no chain rule. We just used power rule. So way 2, let's learn how to do it faster, better, easier, if you know chain rule. Chain rule says, and now can you concentrate? People with laptops open. I'm still not sure if I should allow you to have laptops or not. But if you're paying attention, I guess. So pay attention right now. When I'm taking derivative of 3x to the 7 plus x, everything squared, I'm differentiating this. This is the idea. This is very important to listen and try to comprehend. I treat the function inside as some kind of new function. Let's call it u. It's a popular way to see it. U squared. How to take derivative of u squared? I know that. It's 2u to the 1, right? But we know what u is. So why even keep writing it as u? Does it make sense? Let's just copy it. So I will teach you both ways, to write it with u and not writing with u. You copy, let's keep it in light blue. It was light blue before. You copy the function inside. You pretend you don't know what it is, so you cannot touch it. You cannot differentiate it. Nothing. You only work with the function outside, and the outer function is something squared. So 2 goes down, copy, raised to the 1. And then channel steps in. And channel says it was purple times, and that's what chain rule. That's chain rule here. Times derivative of the function inside. So I'll copy u, and then this one is u prime. derivative of the function inside is derivative of 3x to the 7 plus x, which is 21x to the 6 plus 1. And that is the answer. No need to know and work with the formula of square or sum, distribution, and so on. That is the answer. What do you think about that? Copy inside times inside prime. Times inside prime. That makes sense? And then I will show you how sometimes students do write down the u. It's just kind of more time consuming, so I don't really like it this way, but... Oh, first of all, let me ask you, do you see one is faster than another one? So that's why. Not only that's why chain rule is better, but in general, chain rule covers so many cases when it's impossible to do otherwise. But you can use any method you know in case of the square or cube. That's not a big problem.
Can you please tell the first method, like how you went from the first term to the second?
Oh, the first method, right? It was a plus b squared.
You just opened the square.
Yeah.
Okay.
A squared plus 2ab plus b squared. Interesting that you said open the square. In English, they don't say open the square. But in my language, actually, they also say open the square. Russian language says open the square. And then every time I'm saying it, the people are like, what do you mean? It means like use square of the sum formula. So you see, our languages have common formula notation on that. It's funny. So I had to stop saying that because there was a bad habit here. Open the square, exactly. So let's do one more example, and I will show you how people use the u notation. Cosine of 3x cubed. How do you differentiate cosine with stuff inside? You differentiate cosine, and then you differentiate the stuff inside. That's it. It's easy when you watch me doing it, and then when you do it yourself, there's so many things to question, so practice will matter a lot. Cosine of 3x to the third. This time I will use u, or anything you want. U, w, m. Let's call it the function inside u. Then we're working with cosine of u, and they ask us to differentiate that. And I'm like, okay, I know how to differentiate cosine. So I'm going to differentiate cosine. It gives you what?
Negative sign.
Negative sign. Thank you. Oh, look at that. Interesting. Negative sign of u. And then chain rule says, please don't stop. That's what chain rule says. Chain rule says, well, there's a function inside. It's not just x or t anymore. U is a function. So chain rule says, please differentiate u. So it will be times u prime. That's how it's look. And I will write down where u is 3x cubed. And now the problem is that only you know what u is. It was your choice of intermediate notation. So you cannot present it to people at the conference or even research group. You show up and said, okay, the speed of the rocket was minus sine u times u prime. And people will ask you, where did you get u from? So that is not polite to present stuff without explaining it or going back to the original notation. There's actually some etiquette between scientists. So it's nice. I slowly try to teach people how to use it. Which means you do equal sign equals, interesting. Magic is just happening. Equal. Wow. It's like teleportation in practice. Whatever. No, but I did. I can prove it to you. See?
Yeah, I had a surface, but
I know it glitches at some point. I think it sometimes overheats. So, oh, you know what? I'm just gonna go here. Genius. So I'm gonna write down minus sign, and my u is, I'll put it in different color, 3x to the cube. Maybe I did not make my surface enough complements recently. I noticed it likes complements. So when I do complements, it actually behaves better. Derivative of 3x cubed is 9x squared, and that is the answer. What do you think about this? What do you think about that? So let's review. Derivative of cosine of 3x cubed is derivative of cosine. That's derivative of outside function minus sine of that stuff. Stuff is 3x cubed. Don't touch it. We have no rights to touch it. We did not open the outside Russian doll yet. Or if you see a computer game, you cannot go to the inside next level until you finish the previous level. So now you're opening the Russian doll, and you see inside 3x squared, 3x cubed. So you multiply by the derivative of that function, 9x squared. How fast cosine 3x cubed changes? Outside function fast, derivative of cosine, times inside function fast, derivative of inside. Make sense? So that doesn't click right away usually. The more you work with it, the more you get frustrated, and then it clicks. This chapter clicks with practice. It's just what it is. 17, problem number 3. That is from your, is it 17 a number or 7? No, let's put 17. 17 sine of x squared. So as you can see, like you can do it so many different ways, and you can create so many different examples that I can just torture you with lots of stuff inside of the stuff inside of the stuff. Put fraction inside of this, x plus 1. Boom. Even worse, quotient rule. So you will have it in your home, and then on the master exam. Master exam is created to torture people, specifically rules of differentiation. So whatever we learned this week almost completes what you need to know for master exam, except logarithm exponential functions are left after that. So let's see. The first question, so I will put huge, and let me do for a chance y equals, right? And then I will do y prime. My first question is to see which function is outside. So you need to know the order. It's like onions, outside layer, inside layer, inside layer. You only can first cut out the outside layer of the onion. Which function is outside? 17 sine, right? That's the one that's outside. And they asked me to differentiate 17 sine. We can do that. If your answer is no right now, that's kind of bad. You're supposed to know how to differentiate 17 sine. So 17 sine gives you 17 cosine, plus or minus cosine? Plus. And then you don't touch the stuff inside, you copy it, because you're not ready yet, or the function is not ready to be touched. You need to finish the first level first. So it's derivative at the previous function, not at another derivative and stuff. Then chain rule starts. Chain rule says, okay, this is important. CHR, that's how I start writing chain rule. Chain rule says, please don't stop. I see there's something happening inside. So times the derivative of the function inside. What is the next level I should use? Sine. So I see sine of stuff. I know how to differentiate sine of stuff. It's going to be cosine of that stuff. See? I'm copying this inside piece every time. Then chain rule says, still don't stop. I see one more function inside. And the last function is, and derivative of x squared is 2x. And that is the correct answer. This is what it's called, why it's called chain rule. It creates a chain. They are chained or linked together through this idea of derivative of the function outside, copy inside, times derivative of the function outside, copy inside, times the derivative function inside. Questions? There's a very popular question at this moment. See if anyone can ask this popular question. Questions, concerns, suggestions, critics. Why would you stop? That's what most students ask me. How do you know that I should stop but not keep going? Why not to take derivative of 2x and do times 2 and so on? You stop because the function inside here is x squared. So you don't look at the previous step. You don't look there. You look at the original. Original is x squared is the last step. If you want to take the function, derivative of the function inside of the x squared, do you know what it is? X. And derivative of x is 1. And that's how you know you're done. The last thing should be just a variable left. So we usually don't do that. And then visualization is pretty cute. Check it out. In black color, I will draw the outside Russian doll, Wow, okay. Seriously. Look at this. The outside was 17 sine. 17 sine, right? Then the inside was sine. That's chain rule instead of the chain rule. The inside one was sine. And then there was one more inside, which was x squared. And if you want to see what's inside of the inside one, it's x, the variable x. Here's your chain rule, inside of the chain rule stuff. What do you think about that? How cool is that? Okay, then let me show you something fun, which is, we're gonna do the hard one in a second, but you don't have to write this down. I have this cute idea of higher order derivatives. I showed you it before. You have it in your previous notes, but now you have it in those notes too, because all the PDF files are in modules. Distance, velocity, acceleration, jerk, snap, crackle, pop. We actually have official AC video that has a name, Don't Be a Jerk. And they mean don't be a third derivative. So very interesting. Oh, actually it's missing it. It should be S prime prime prime. And that's usually used in physics. Math people don't know this. So I googled in Wikipedia, that's why I find out about it. It was kind of fun. Find A if S is given. That's the students' most favorite topics. They are talking about distance. Distance is given as cosine 7t squared. 7t squared. And then they ask you to find acceleration. Do you know what they're talking about?
Yeah.
What? Second derivative. The first derivative is called what?
Speed.
Speed, velocity, right? Both, wherever one is better than another one. So let's make a note. We know that A is derivative of V or second derivative of S. So you just need to know that. At least students usually know these three. That's good enough. So in the end of this class, we're gonna learn how to go back from acceleration to distance using integration. It'll be very fun. Usually students like that too. So let's do it. Step one, let's find first derivative. First derivative, which is called velocity. Maybe let's make it professional. Of t time. That is velocity of time. And this is when you see the chain rule happens. Cosine is not just of t. It's not cosine t. It's cosine of the function. You can call it u first, and you can see it's cosine of u. You know how to integrate cosine. It's going to be what?
Negative sine u.
Negative sine u, and you can say it out loud. And then you save your time and you plug your u right away. U is the original, so you copy the function inside. And then you're done, but then you realize that you don't get points for this problem because it's too early. You never differentiated 70 squared. That's why it should give you a hint. Probably you forgot something. Times, exactly. Chain rule steps in and says, please continue. Derivative of the function inside. So if copy was u, this is u prime. Let me put it in red. If u was the function inside, now we're going to find u prime, where u was 7t squared. Gives you what? 14t. That is the answer. You can relocate things to make it more pretty, like minus 14 sine 7t squared. Usually we put constants in front, then t, then trigonometric functions. But the answer is correct, so you don't have to do that. Now let's find another one. Let's find A. A is second derivative of S, which is first derivative of V, which is called A. I forgot T everywhere. Acceleration. Let me see. I have this. Keep calm and do more calculus. See, if you're freaking out at home, that's my message. Keep calm and just keep trying. Because you will be frustrated with this homework, but when you succeed, it's actually very satisfying. When you get it, it's satisfying that you get it. So keep trying, don't get demotivated. Everyone struggled with it, so it's your turn to struggle. Equals. Now I need to differentiate this. Maybe it's smart to put it in the box. So your eyes visually can concentrate on this. It's a very good strategy, psychological, to put important stuff in the box so your eyes can concentrate. How to differentiate that? What do you think?
Again, but
What?
Product rule. Product rule.
Product rule, product rule, product rule. Yes, people at the end. Product rule. We just learned it on.
Product and chain mixed.
And then chain rule while we're doing product rule. Exactly. So that's going to be product rule, chain rule mixed together. Your homework is due tonight, remember? It has product rule in it. So I hope you're good at this. Okay, fine. So let's figure out what is U and V. But that's not the U1 in the chain rule. It's going to be one function. Let's call it U times another function. Let's call it V. So U times V prime gives you U prime V plus U V prime. You don't have to memorize it. Your job is to know how to do it. Nobody will ever ask you formula for product rule or quotient rule or chain rule. We don't ask you for formulas. We ask you to do stuff. Those are rules. So they are just tools to know how to use. U prime, do you need the formula or not? U times V is U prime V plus U V prime. I highly recommend to start with U in both product rule and quotient rule. See, it just doesn't like me today. Look at this. Good. U prime means I need to differentiate minus sign. What is derivative of minus sign?
Minus cos.
Negative cosine minus cosine. But what should I do with 7t squared? Just copy it. Remember, because it's function and sign, right? It's still that u we have from the previous calculations. Like so. So let me copy 7t squared, maybe in red. 7t squared is still copied. And I'm not done, because I did not differentiate 7t squared, so I will do times, and that's chain rule here. Derivative of 7t squared is, again, 14t. And that is just u prime. That is just first derivative in the product rule. Second part says copy v. So I just did the u prime. Now it's time to do copy v. Well, that's the easy part. I just copy it. Copy v. Well, let me not put this copy because now we have copy in the chain rule. Plus copy u. Okay, that's easy. I know how to copy. Copy paste minus sine 7t squared. Make sure you have enough parentheses. Times derivative of v. Here it is. Derivative of v. That is 14. And that is the answer. If we don't ask you to simplify, you're good to go. That is the answer. Ask me, what do you think about this? How cool is that? So when I say how cool is that, I have proofs that it is cool. But what do you think about that? The function derivative of u required chain rule. So let's do it. It's quotient rule, not quotient, product rule. It's product rule and chain rule. That's what just happened. Product rule and chain rule at the same time. Can you do that? Like, how cool is that? Questions, ideas, suggestions? Ask me about this. How did we differentiate the box in yellow? The result is in box in purple. What do you think? How do you feel about this? Yeah, but unfortunately, it looks very nice when you see someone doing it. It totally makes sense. When I was learning, it totally makes sense when I watch someone doing it. And then when you have to do it yourself, it's surprisingly not obvious at all. But it's not very hard. It's just a little bit hard. Just letting you know, you can do it. Let me show you some cool stuff and then ask you to work by yourself about a little bit. So I have this cute animation. The image processing and image recognition is done by the artificial intelligent AI. There's a data science, data collection is involved, blah, blah, blah. Kind of now, I think your generation knows about much more than whatever I was teaching 5 years ago. Whoever I was teaching 5 years ago. But the idea is, how does your smartphone unlocks you show your face, and it's have to go through levels of checking whatever is matching with the data of the computer. So in this case, they show a dog and a cat, and it's kind of hard to explain what's the difference between a dog and a cat to a computer if you think about it. I always say, try to explain to a blind person, what's the difference between a dog and a cat? They all have 4 legs and a tail and the ears, and sometimes they're the same sizes. Sometimes a dog is smaller than a cat. So how do you know? They have fur and different colors. That means it took so much training for a computer to try to recognize the answer. And it never gives you 100%. At every step, input and output, you see the hidden layers. At every step, it does some kind of mistake calculation or error calculation. And to do that, it uses chain rule. So at every step, it does chain rule and chain rule and chain rule, collects all the errors together, and then it has 7 different outputs. And the output with the less collective error will be the one they chose. And they will say, it's a dog 98.5% accuracy. So that's how it works, yeah?
It's really fun. It's just like a machine with 100 million different levers that you don't know what any of them do, and you just flick one of them and say, is that more accurate than it was before?
Isn't it crazy?
Flick a random other one and you're like, is that better than it was before? And then you flick a random
Exactly. Isn't crazy? It has input layers, hidden layers, output layers, and the hidden layers sometimes, like you said, thousands and thousands of steps. And then every time it says, okay, the ears are looking like this. More probably the dog than the cat. And it has a tail. Is it long? Is it short? And keep checking and keep checking. On every step, it takes partial derivatives. We're going to learn them in calculus 3, but it is chain rule and chain rule again and then chain rule again. And while it's doing chain rule, it puts weights on every step, and the weights are errors or confidence of the output. So it's called backpropagation. It's an extremely cool topic. And the first image recognition computers were done this way, specifically like that. Then the methods improved a little bit, but it uses chain rule all the time. So cool that in calculus 1, we already teach you what is used by AI. And it cannot go around it. It uses derivatives. It asks how much this picture is close to whatever I need to know. And it has thousands of pictures of dogs and cats, and keep comparing to some kind of qualities of each. So that is a pretty cool idea. I always like this idea. It's called backpropagation with weights, and the weights are errors or mistakes. So you see, you should not feel bad when you make mistake. Mistake puts a weight on your knowledge. The same as AI puts mistakes as weights on each output. And at the end, you just produce some kind of result with some kind of error, and you just minimize the error. So this university, actually our math department, is collaborating with Mayo Clinic and working a lot on the neuroscience projects mathematically and using AI. So Mayo Clinic gave us, with lots of privacy permissions and signatures, you even need to do fingerprints and go through the background check as a researcher. That's what I did. To look through MRI images, and you have thousands of MRI images, and you feed it to computer, and computer now gives sometimes a better results and faster results than a doctor. Because if you can train a doctor what to look to find a tumor in the brain, computer can do that too. So computer will give the result saying tumor is here with 75.3% accuracy. And then for a doctor, it is to decide if this accuracy is enough to proceed with the surgery at that location. So that's how fascinating it is, and we're doing it right now in our department as a research. So that's chain rule for you. And then the last 5 minutes, 7 minutes. I want you to work together on, I know, right? Damn, no. On this problem. Work together in groups, and I'll walk around to make sure that you're not procrastinating or ordering something from Amazon. And there will be more examples in the future, chain rule twice. Lots of examples from your homework, but this one, let's do it together.